basic introduction to the language we're going to use was covered in the first 3 lectures. Today, in the abridged lecture, unfortunately, we discuss one of the 2 main motivations. Motivation, that is moduli sticks. The other one is the étale topology, cohomology, and I hope we'll find some time to discuss them as well. Today, however, I'm going to discuss mostly the set theoretical nature of the moduli problem using the language we have developed. So, first, some generalities that will look as follows. Suppose C is an essentially small. We mean that it is algebraic. It belongs to the algebraic geometry, but I don't know how to express it in the formal way. So our categories will appear in a series of examples. So our main question is, well, perhaps I can denote it now in the most general form. We are going to try to find the subcategories of our main category such that, and I'm putting the question mark here so that we see that we are just looking for such subcategories, and I must admit that they exist in a rather, or are known to exist in a rather limited class of cases. However, we are going to concentrate mostly on one of them. So we are looking for such subcategories that, let me remind you our technical and short notation, like this, something like an absolute value of category or its catalog should belong to the same category. Maybe this condition can be used instead of this one, this imprecise one. During the previous lecture, I just claimed that algebraic geometry is a unique domain of mathematics in which the classifying objects belong to the classifiable category. So this is the general goal. And the first step is to select such a subcategory that its set theoretical part is well defined. Let's just once write it in a long way for get full functor from our C to, or rather C not to the category of set. That means just considering such a category set theoretically. So we are looking for the cases where it coincides with the general forgetful functor from the original is an object. It should be an object of the forgetful functor from our C to the category of set. The formula is long and complicated. May I just having written it down, repeat what it means in the plain language. This catalog going to be considered as an algebra geometric object should be first defined set theoretically, and after that we consider the structures on it that turn it to the underlying set of some object of algebraic geometry. Sorry for this general formulation that should clarify the approach, but it is not so long as not so clear as we would like it to be. However, I hope we clarify it, specifying it step by step. First of all, let us try to define the large categories named C here. As I said, and as you perhaps know from other sources, algebraic geometry is a rather extended, rather large domain, and I'm not assuming very well acquaintance with it. So we specify some classical versions of it, and perhaps start with a purely algebraic approach to the problem. For that, we fix as we did before, an algebraically closed ground field K, and consider for C the category of finitely generated fields over this chosen field K. And we have developed all the details of a formal language that allows to do it compactly, finitely generated. We consider the extensions of the ground field like this, and as I briefly mentioned before, the whole thing, the whole object of study is close. For the time being, I'm writing down something imprecise, but I will do it precisely just in a while. So it is the birational. Studying these extensions is exactly the same as studying birational algebraic geometry over K. In fact, this basic question, this basic statement is very close to the precise one, and it means that whenever, say, denote as K calligraphic and K calligraphic prime the objects of this C, that means exactly that they are the extensions of K, and let's write it traditionally in the form of such diagram, popular in the language of field theory. And well, it means exactly that K is a subfield of K and K prime. So the morphisms in this category are, the definition of morphism is obvious, and therefore the definition of the isomorphism in this category is obvious as well. And now on the geometric side, whenever we have x and x prime, a quasi-projective and what is most important, irreducible. Varieties. Over K, then they are birationally isomorphic here we should use the specification of the type of isomorphism. So they are birational isomorphic, birationally isomorphic, if and only if the fields of rational function of them, in order that these fields be defined, the varieties should be irreducible. And they are birationally isomorphic if and only if their fields of functions are isomorphic. So here I use the standard notation for the fields of rational functions. Let me remind you that such fields are defined as the fraction fields of any ring of regular polynomial functions on any small enough Zariski open sets of these varieties. So the long and classical definition of birational isomorphism means that there exist such embeddings of these varieties that this isomorphism is defined by tuples of rational functions defined almost everywhere, but I prefer just this algebraic definition of it. And perhaps I should mention here that this specification of birational isomorphism is important, since there are other kinds of isomorphism. Biregular would start with the same 3 letters. So let it be birational like here. So the problem of classification quasi-projective varieties up to finer isomorphisms is much more complicated. As well as we don't restrict ourselves by some special classes of varieties, like, say, smooth projective. In the simplest cases in which we develop this approach, the classification problems are equivalent. The birational and biregular problems of restricted to smooth projective varieties are equivalent. Okay, so this is the main class of algebra, geometric categories. Now, what kind of categories can be found in them that for which this inclusion works? The general idea for which I have perhaps some place here is as follows. General hope that I again formulate in some imprecise sense is that C naught is C with some fixed, let's write it like this, fixed, discrete, invariance. So in every case we should, of course, present the list of such invariants, and one of them is, of course, the dimension, starting with dimension of the manifolds. Let me write down, let me use the notations that were just used, dimensions of the varieties that have the purely algebraic senses as the transcendence degree of the fields of rational function over the ground field. Okay, so I'll ask about your questions in a while, or no, I have to ask you now because I have to erase something. So any questions or comments now? Well, so I keep the general task here, and define a large class of examples of discrete structures. So a large class of discrete structures is defined over the ground field of complex numbers. Here the discrete structures, one of the most natural discrete structures is a fixed topology, for example, and perhaps I should confess that I don't know any other naturally defined examples. Well, in some cases there are, like, say, groups of automorphisms, but this is historically and mathematically the most productive way. For example, topology. In the language we are using, that means that we pay special attention to the forgetful function, functor, from C varieties. Oh no, we didn't introduce it, but let's introduce it now. So, varieties. Sometimes we can avoid specifying the type of varieties we mean, but the quasi-projective ones will do. So we forget not the structure on a fixed set completely, but we consider the possible structures, algebra geometric structures, on the fixed topological space. The situation is rather simple, classical, and beautiful in dimension 1. I can say that everything is clear. What does it mean? The image of this forgetful functor, just for simplicity, let's decide that we are speaking about smooth, complete curves in this case, and we know all the underlying topological spaces. They are the oriented surfaces that are very well classified and are just the oriented real surfaces. So we know the image of the forgetful functor, and our main classification problem turns into the question of having a topological model of, for example, surface of genus 2. What is the set of complex structures or algebra geometric structures that can be considered on this surface? But the clarity diminishes quickly, and when the dimension is 2, the image there is a great image, the great problem of image. I am just trying to write it in one word. That is, the question is, what is the topology of complex algebraic surfaces? Lots of manuals and conferences are devoted to this problem. These question marks mean that they are by no means, the question is by no means solved completely, but there are lots of deep and interesting results in the great topological theory of four manifolds. Just even forgetting about algebraic geometry, we could discuss the classification of four-dimensional real compacts. So lots of results and lots of open problems. And well, when we know, and I should stress that there are lots of intermediate questions. The most striking of them is the existence of smooth structures on a given four manifold. I mean, when it is it carries a structure of smooth algebraic variety, it is at the same time smooth as a topological space, and is a variety. But in some cases, in fact in lots of cases, this variety would not admit a smooth structure. And if it does admit one, the problem of describing all of them is very hard and not always solved. And as for higher dimensions, perhaps I should just suggest several question marks. Most of the natural questions are open. This is one of the reasons to concentrate in more detail and return to our general problem of classification in the case when at least over one field we have a simple and clear picture. Any questions now? Okay, now I give the answer in this case. So let's agree that by a dimension in generally we mean any of these dimensions. So for dimension 1, the result is as follows. The C naught here well, for an integer G is n, G being chosen to denote the genus. We can choose the C naught as being K variety, K variety. Our notations are not completely fixed, so let me use it again. The varieties over K denoted by the traditional letter X, such that the dimensions of X is 1 and the genus is J. Maybe there are somebody here among the listeners who understand the genus mostly over the field of complex numbers as a number of handles of a surface or number of holes of a surface that is the same as the half of the first Betty number. In fact, as for the goal we are not discussing today, that is introducing the appropriate cohomology theory over arbitrary fields. This goal is to develop the theory, perhaps one of many possible ones, of such cohomology that Betty numbers still make sense, and we could extend the understanding of genus as of the half of the first Betty numbers to the curves over arbitrary fields. However, this activity is quite involved, and the alternative definition is just the dimension, of course, over the ground field of the first cohomology of the first cohomology of X in the coefficients of the structure sheaf. The other advantage of this definition is that it extends to the singular curves, and sometimes we need this extension. So in this case, let me remind you what was already formulated. That is, whenever we consider the category of the field extension of the ground field with transcendence degree over K being 1, then this is an essentially small category, and its catalog itself does not belong to the objects of this category, but is isomorphic in any reasonable sense. Let's use it set theoretically and not every time write it. So this extension that I'm going to write down can be understood in any categories of what we have discussed. The category, the objects of Mj of K, where M sub J of K belong to the same category. Well, of course, not the same with one, but well, they are just varieties over K. And these varieties are quite enigmatic, загадочные, deserve lots of attention during the last decades, and as we are going to see perhaps today, just the deeper study of them demands going beyond the set theoretical mathematics. And this is what we are going to start discussing now. Any questions about what was said up to now? Well, then I erase perhaps everything. And remind the problem from the last lecture that was promised to be formalized but was not due to the obvious non-mathematical reasons. Some events during the last week. But I remind the formulation as a set, so for any J. The set, unfortunately, we have to still to write it in a long way, or get from these varieties over C to set is of of M sub J. I'm just saying that maybe let's fix our, let's write it just here. By our definition, it is the set of algebraic rake or by Riemann existence theorem. It's the same thing as complex structures on let's introduce the notation. S sub J is just the topological model of the surface of genus J. S sub J. So this is the set up to isomorphism. Sorry, the isomorphism is there under the braces. The word structure just means up to the isomorphism. And it was claimed that this set can be described in a transcendental way using another type of catalogs, that is the topology on the space of metric that we ignore now, and we consider just the set of Riemannian metrics on S sub J. Well, then I should emphasize here that though S sub J is defined in a purely topological way, the standard theorems tell us that unlike the situation in the topology of four-dimensional manifolds, this topological surface carries the unique smooth structure. Therefore, instead of among all the metrics on it, we can consider Riemannian metrics and factorize them by the group that is interesting by itself, and it is the group of smooth functions on S sub J that is being acted upon by all the diffeomorphisms of S sub J. However, we take just the half of this diffeomorphisms, those respecting the orientation. And this group acts on the space, infinite dimensional space of functions. the space of functions acts on the remaining set of remaining metrics on Sj by multiplying their infinitesimal elements by the exponents of the functions in every point. And what is not at all obvious, that this factor is finite dimensional as soon as we impose the most natural structure there. Maybe let me say more about that. Riemann metric is sits in the set of all metrics on a surface, and as such is a cone on the real valued positive functions on the square of a surface. So it sits in the Banach space or topological linear space, and the action of both groups are smooth. So here we have three infinite dimensional objects with a well-defined smooth structure. Therefore, we can consider everywhere the tangent spaces, and the whole factorization can be described on the infinitesimal level. And the factor, infinitesimal factor, turns out to be finite dimensional. So this statement, maybe this is the only construction in the modular spaces, theory of modular spaces, where the considerations are not trivial, even in the case of genus 0. You can consider all these objects on the sphere, in particular working with the remarkable group of diffeomorphisms of sphere. And they also deserve attention. However, this factor defined like this is obviously carries some obvious structure of smooth variety, carries less obvious structure of almost complex variety. I do not go into details because it's not so important. But this, so you can skip my 2 sentences about that. The non-trivial fact is that this almost complex structure is integrable, therefore gives a complex structure, and then it is a separate task to prove that this complex structure is the underlying structure of algebraic variety. In fact, every step is non-trivial here. However, we want to do, as you like, more or less than that. We are going to skip the intermediate steps valid only over a field of complex numbers and reach the algebraic structure on the moduli space immediately. And we wanted to make sense over a purely algebra geometric sense over an arbitrary field. Sorry, I should put C here. as well. Okay, now we say a few words about the general principles of imposing the algebraic structures on the moduli spaces. To do so, we first need to introduce the concept of deformation. Deformation of algebraic varieties. And I'm afraid that to do so, we should fix three kinds of writing down the same letter. I'll try to write down the most calligraphic B, deformation, yes, perhaps B, and it's going to be a category of bases. And the whole history of the subject tells us that we should avoid making some solution about this category now. I could say, for example, let's consider the smooth algebraic varieties. And then it can turn out that we need nilpotence in the structure sheaf. So we better consider the schemes that are not necessarily reduced. Or when we come to the essence of our course, we can find out that we restrict ourselves essentially considering this category as a category of sets with additional structure, and we better consider something more general that in fact are Grothendieck topologies. So these are category of bases. The main word here is basis, and then according to the notations taken in this course, we denote, try to denote our varieties in the thick font, and then we are going to make a distinction that it is very inconvenient, so sometimes breaking some rules we'll use B small instead, but ideally we use these three kinds of capital B's. So we want to define, and sorry, I have to distinguish between two algebra geometric categories. As I said, for example, this B calligraphic can contain the objects with nilpotence, non-reduced schemes. I admit that some of the listeners are not quite fluent in these notions of like non-reduced scheme, and I don't give an advice to find all the answers in the text where they were introduced. There is Grothendieck volumes, just because they are terribly thick and difficult to read. But hopefully, when we need it, I'll define it. And what we are going to classify is simpler, and we have already fixed some letter for it. So suppose we have, let me write again the word. Suppose we want to define a deformation of a certain object, say x naught, belonging to our C. And the concept of deformation is quite universal. It is the morphism of some objects over B, and of course this is a morphism, unfortunately, in the large category, in the category of bases. However, these categories, the general picture is like this. Here is the B in this bold font, and instead of this difficult B in different font, it is traditional to use the letter O. And here is a morphism in this category. The letter pi is quite traditional. The real number pi is never in the conflict with this notation. Basically, deformation is such a family with the condition here we have it x naught with the fiber over B. So x naught is, well, said theoretically, it is just the pre-image of the point O, and the other fibers are its deformations. But there are two foundational issues, and let us don't skip it. Let me emphasize that this object is defined only set theoretically. and said theoretically it is really so. And this bullet means that we have to define the fiber x naught is defined in the following maybe strange way, like we have the general family over our B. Now, a point here is, well, from Grotendik's point of view, sorry, I should move this triangle. As you know, Grotendik always thought in terms of arrows rather than object. So for him, such a concept as set theoretical preimage, or even an element of the points, sorry, this is incomplete, let me write it again. What I'm going to say now is maybe trivial, but very important to understand Grotendik's philosophy. So, a point in a topological space is a wrong concept. The correct one is a morphism of point living somewhere into the algebra geometric objects. And as for the concept of point, we use the fact the Grotendik's relativity that was introduced a couple of lectures before. Everything is defined over something, and the analog of point is just a spectrum of the ground field. And this arrow can be just called O. So what we usually consider as a point in a variety is for Grotendik a morphism of something like a point into the variety. So we can call it O, and then X sub O is nothing but the fibered product of this pair. So you should think about it. Think about it to just to see, to feel yourself an obvious construction from the classical mathematics, from the Grotendik's point of view. And this is just one issue, and the other is that in order to be deformation, the other points, consider, say, random B is here. So there are other fibers, other X sub B's should be, well, in fact belong to the same category, but let's be a bit imprecise here and just demand that there are similar to X sub O's. Perhaps I give an example in a while. In fact, I'm avoiding the vicious circle, порочный круг, because we are trying to define C knots we are going to work with. Therefore, I don't want to use the expression that other X sub B's belong to the same category. So in the abstract, now it can be formalized in two ways in the abstract algebraic geometry. We demand that pi should be flat, and I'm afraid that it needs several years of thinking to not just to learn by heart the definition of flat morphism in terms of some homological functor, Tor, called Tor, but just to feel it, and you need to consider lots of examples. The other way is to consider it O or C as in classical terms, so the whole thing X pi to B should be supposed smoothly a fiber bundle. So I understand that I behave not completely honestly avoiding the precise definitions of the central objects of our considerations. However, in the particular cases, we are going to be completely precise. Any questions about what is written on the blackboard now? Okay, then until the close end of this shortened lecture, we discuss the central example, families or, as we know, it is the same thing as deformations of curves. here, unlike the previous definition, the case of rational curves has no interest at all, and we assume that J is positive. So, considering G1, the first and very good example is the family of curves defined by the equation I'm writing down. Well, maybe be with the infinite point. In every fiber you can add infinite point. We'll always denote it like this, the equations become a bit longer, so I avoid it, but I hope everybody who heard something about elliptic curves understand the matter of the infinite points. Now let's fix the actors of this family. So this our base here is what I like to denote in a bit non-standard way, double dotted K. It would be better, just one in our life, to denote it officially as A sub 1 of K. That means a fine line over K, where it is no more a field, but torsor over the additive group of the field. And I want to put double dot here and identify it with a shorter notation, K double dotted. That just means K with two punctures. So first of all we should draw it like this, and here is the T line, and here is 0, here is 1, and everywhere we have an honest, for any T here, we have an honest cubic curve. In one of the standard forms called sometimes Legendre cubic. This is just the equation of Legendre cubic. But it is different. So this is over general T, but it degenerates here over 0 and over 1. In an obvious way, the curves become rational. And well, this sits in A3 of K, and pi is simply the projection of x, y, t to t. So here is the main deformation, and then due to the time restrictions, the last thing I see now is that the same object over y square equals x minus 1 minus t 2. In fact, sometimes we can use the shorter notation and draw here the C doubly dotted, and I want just to claim that it is one of the most remarkable objects. From several points of view, you can consider the periods of first of all, it is immediate that this is a family of curves of genus 1. By the way, with some efforts, you check that all the curves of genus 1 are among the fibers of this family. And what I've said just now is valid over an arbitrary field, but over C, when you say consider the periods of these curves depending on T, you get into the domain of the most classical functions. Hypergeometric series satisfying the classical differential equations, and so on. As soon as you turn to the uniformization of such a family, you run into the other basic objects of complex analysis and arithmetic geometry. You meet the simplest modular functions here, and perhaps so on. I think this list could be considered, and at the same time it is the simplest case of the families we need to classify curves. So we have to stop now. Any questions or comments or suggestions? So perhaps now, then hopefully see you in a week, hopefully, because nobody can be sure in anything nowadays, but since all of us are fixed, at least in Russia, we can meet physically, so I suggest that anybody who is able to reach this 303 physically, please do it. It is a bit easier to speak with some people than with the rectangles on the screen. So then, until next Monday, bye.